Ladies and gentlemen, welcome aboard the Smithsonian Boeing 747. This will be a short 30-minute flight. We'll be cruising through the four forces of flight and composite materials. Flight attendants, prepare for departure.
Hi, I'm Beth Wilson, and today I am with our chair of the Aeronautics Department, Bob Vanderlinden. Bob, how are you today?
I'm fine, thank you. How are you?
Good. Bob, can you tell me where we're sitting this morning?
We are sitting in the cockpit of a Boeing 747.
And why do we have a Boeing 747 in our collection?
Well, we have a 747 here, so our visitors can get some idea of the scale and scope of what a modern airliner looks like.
And now we only have the nose cone, is that correct?
That's correct.
Why just the nose cone?
Well, primarily because the rest of the airplane would not fit in this building.
And where did we get this airplane?
We got this airplane from Northwest Airlines.
And do you want to show me exactly how big the whole airplane is?
I'd be glad to.
Thanks, Bob. So this is just 35 feet, the nose
Yes.
cone. And so what, is the plane double that size?
It's a bit bigger than that.
Well, how about I start walking?
Why don't you?
Tell me when.
I will.
Okay. Here, Bob?
Keep going.
How about now, Bob?
Almost there.
How about now, Bob?
There you go. That's it.
Okay, so how do you get a plane this big off the ground?
That's the four forces of flight.
This is Steven 30. Hi, I'm Beth Wilson, and I'm coming to you live from the America by Air Gallery at the National Air and Space Museum in Washington, D.C. And in this gallery, we take a look at the history of commercial aviation, beginning with early mail planes, going all the way to our Boeing 747 nose cone. Now, Bob and I talked a little bit about how we get a plane this big off the ground, and to help me cover the four forces of flight, I've got Marty here. Marty, do you want to explain how we get something this big off the ground?
Sure. So we're going to talk about the four forces of flight. Those are weight, drag, lift, and thrust. So let's start with what keeps us on the ground, and that's weight. So weight is simply gravity pulling us back down towards the ground. Now everybody, look around. Is anybody floating around up there in the ceiling? No. Gravity's doing its job. It's pulling us back here to Earth. So in order to fly, we've got to counteract that weight. The next one's drag. And drag is the opposite motion that we want to go. So if we want to go forward, drag pulls us back. And that's caused by friction and differences in air pressure. Now that's kind of hard to understand, so I've got a little demonstration here. I've got two pieces of paper, they're exactly the same. But if I take this one and I wad it up and then drop them, Newton's laws tell us that these should hit the ground at the exact same time. But watch what happens. The wadded up paper hit way faster than the one that stayed flat, and that's because of drag. The friction of the air coming down with the flat one caused it to go slower. So those are the two forces that keep us on the ground.
Well, that's very nice, but that doesn't tell me how we get up into the air and stay there.
Exactly. So it takes two other forces to get us up into the air and to keep us there. The first is lift. Lift is the force that pushes us up into the air. And it's caused by differences in air pressure. So let's take a look at this airfoil. This is an airplane wing that's basically been chopped up like a loaf of bread. The bottom of this wing is nice and flat, the top is curved. Now pressure pushes down on all sides of this wing all the time, but as it flies through the air going over the top gets squeezed down and goes faster, and that creates a low pressure area over the top of the wing. The high pressure underneath pushes that wing up into the air. That's kind of confusing, isn't it?
Do you guys get that?
Let's try an example. You guys all have a strip of paper in your hands. Hold those up. We're going to put them up above our top lip, and we're going to blow. Okay, what do you think is going to happen? Is it going to go up or down? It's going to go, okay, let's see. the paper went up. And that's simply because we blew air underneath it and pushed that paper up. Now, we're going to hold that same piece of paper under our bottom lip, and we're going to blow over the top of it. What's going to happen? Is it going to go up or down? Everybody says down. Let's try. The paper came up. That's because we caused that air to go faster over the top and create a low pressure area. Underneath, we had higher pressure that pushed that paper up into the air. So that's lift. But that's not the only force that we need. We also need thrust. If you take a look at this propeller, it's shaped like an airfoil. When we turn that on its side, it gives us forward motion, which is thrust. So lift gets us into the air, thrust keeps us in the air.
Okay, and you said that propellers create thrust.
Yes.
There's no propeller on this airplane.
There are not, but a lot of the same concepts are used in jet engines. If you look at this cutaway of an airplane jet engine, you'll see that on the inside is a series of airfoils, just like this propeller, and it pulls that air into the engine, creating thrust. So we create that thrust to get us up into the air. Now, this plane is significantly different than the Wright brothers plane or any plane with a propeller. The designs have changed dramatically in the last 100 years, and the materials that we've used have changed a lot, but those 4 forces of flight have stayed the same.
Okay, so every single airplane in this gallery relies on the 4 forces of flight to get us off the ground and to stay in the air.
That's exactly right.
Okay, and I think we have an online question. Can we get an online question? How do helicopters work the same way as airplanes?
They do. If we look at the propeller again, you'll see that it looks very similar to what's on the top of a helicopter. It's got these airfoils, and when it spins, it creates that low pressure on the top, higher pressure underneath, because the air going over the top is faster, low pressure there, high pressure underneath, and it gives us lift that takes the helicopter up into the air.
So a helicopter works the same way, it's just a little different looking.
Exactly.
Okay. Now, today's show, we're going to talk about composites. But before we get started on the composite part of it, I've got a 30-second challenge for you all. So let's get started with that. Okay, so does anyone have a guess of what this might be? Just a guess. Give me a guess. Go ahead. What do you think it is? It is. It's part of an airplane, okay? This is actually part of a composite airplane, and you can see it's like really light, but it needs to be very strong in order to build an airplane out of it. So we're going to test this strength, and to do that, I need a volunteer out of the audience. You want to come up? Come right here. We have this. Hold on a second. We have this, but we have to be safe because you know you're going to hit this. All right? We don't want pieces to go flying into your eyes. So on the count of 3, all right, hit it as hard as you can. 1, 2, 3. Well, that little hammer didn't do much, but keep them on. What do you think about this one? Do you guys think this is going to do it? 1, 2, 3. What do you think? No, it didn't break, did it? So not only is it light, but it's also strong. Right. Now, we don't have a composite plane in our museum here, but our friends at the Museum of Flight in Seattle do have a Boeing Dreamliner, and their chief curator, Dan Hagedorn, is going to show us some of that plane right now.
I'm Dan Hagedorn, curator here at the Museum of Flight at historic Boeing Field. The The beautiful Boeing 787 Dreamliner that you see behind me represents the state-of-the-art in composite technology. I'd like you to come on board with me and take a look at some of the wonderful things that composite technology is going to do for you as a member of the traveling public. When you get up close and personal to the 787 Dreamliner, one of the first things you recognize is how extremely clean and smooth the fuselage of the aircraft is. You won't find any of the traditional wrinkles, rivet lines, panel lines, and so forth that you find on traditional metal-built aircraft. You will find about 6 times on the aircraft the joint seam, however, where the different barrels, as they call them, were joined together to form the fuselage of the aircraft. These are extremely smooth, however, and extremely strong, and contribute significantly to the efficiency and fuel economy of this aircraft design. One of the most interesting engineering developments in the Boeing 787 Dreamliner are its wings, which of course are also made of composite materials. One thing that's noted by passengers and those on the ground alike is the incredible degree of flex in the wing structure while the aircraft is in flight. It's often referred to when you look at the aircraft nose on as the Boeing smile. When Boeing was testing the engineering on those wings, they flexed as much as 25 feet at the wingtips, displaying not only the rigidity of the wings and their ability to flex, but also the fact that they gave a much more comfortable ride to the passengers on board the aircraft without any risk to the aircraft whatsoever.
Okay, so that is a quick view of a Boeing Dreamliner, and we are going to talk more about composites now, and I'm so lucky to have material engineer here, Arlene Brown from the Boeing company. Now, we've been talking about airplane composites, but obviously these aren't pieces of airplanes. Do you want to tell me why we have this out here?
Yeah, if you make something that big, you really want to be able to recycle it.
Right.
So it turns out plastics, the type that are in water bottles, for instance, those will melt and they're easy to recycle. But this is basically an epoxy composite in our airplane, and so we needed to develop a method. And so, for instance, the raw materials can turn into something like this if we have some excess. Or we can even take the actual finished composite parts, like when we cut a circle out for the window, and another company can go chop them up and turn them into parts. And this is actually chopped fiber that originally came from an airplane, basically.
Okay, so what you're telling me is that I'm not going to find a Dreamliner in one of those airplane graveyards. You can recycle it.
Exactly.
Okay, so I think what we'd like to do now is take a look at actually how we make the parts of the airplane using composites.
Glue-like epoxy resin is already on this slick carbon tape that is being put onto spools. Spools feed the custom carbon tape into a robot head. This automated fiber placement process allows us to place composite material where it's needed and in the direction we want for efficient design. Using heat and pressure, the robot head lays the tape onto a rotating barrel. The barrel is sealed under bagging materials and the air removed. It is then baked in one of the world's largest autoclaves. An autoclave is a giant oven that applies pressure. Once the part is done baking, we remove it and take off the bagging. The part is then inspected and joined to the other airplane sections. This process allows us to make large integrated structure and minimizes waste while optimizing strength and stiffness.
Okay, Arlene, so I have a piece of composite here, but what you have are the raw materials. So do you want to tell us a little bit about what these are as compared to this?
Oh, I'd love to. So this is epoxy resin, otherwise known as glue, and it actually is basically kind of a liquid form, though, when we marry it up with the carbon fiber. You just saw the carbon fiber on those spools going out. And those spools actually have a little bit of this in that fiber. And then what we make is something that we sometimes call prepreg. And we take this material, and this is what the form is when it goes into basically the autoclave, which is a giant oven. When it comes out, it looks like this.
Okay, so this baked is this, but this is really smooth here, but my piece, it looks like it has fabric in it. This doesn't look the same. What What's the difference between this and my actual airplane part?
Well, the thing that we call reinforcement, instead of just being one piece of tow, is actually woven into a fabric in kind of the same way that your clothes are actually woven.
Okay. Now, the students that we have here are from Jefferson Academy, and they actually built some composite materials and ran some experiments. Would you like to take a look?
Oh, that'd be terrific.
Okay.
All right, guys, today we are going to test our composites, and I can't wait to see how you guys did in building them yesterday. So let's review a little bit. A composite is any material that's made of two or more materials put together, and it gives it a different characteristic. For example, today we're going to be testing some composite materials that you guys made. Now, the first test we're going to do is what? What are we going to test first? What are we going to test first?
We're going to test the two pieces of
Yeah, we're going to take two pieces of cardstock and we're going to test them. We're going to lay them on top of each other and test how much strength they have. Is that a composite?
No.
No, it's just the same material. It just happens to be two pieces of it. What's the next thing that we're going to test? What are we going to test next?
Two cardstocks that glued together.
Yeah, we're going to take two cardstocks and you guys glued them together yesterday. Is that a composite material?
Yes.
Yeah, because it's got two different materials combined and we're hoping that it increases the strength. So what was the third thing that we're going to test?
Cardstock, fabric, and glued together.
That's exactly right. A layer of cardstock, glue, a layer of fiberglass cloth, more glue, and a layer of cardstock. So let me show you guys how we're going to set this up today, and I'll use this as our example. You guys all built your testing apparatus yesterday, and the way that you're going to do this is you're going to come over here, you're going to reach in and pull your string up, and then you're going to slide this through it. Everybody see that? Then after you do that, you're going to come over here and you're very slowly, remember, very, very slowly, you're going to pour that water into the funnel. We're going to weigh this before we start to get a baseline on it, and then we're going to weigh it after it fails to see how much water it held, see how much weight your composite was able to hold. You guys ready to start?
Yes.
All right, let's get started. Look at it flexing up there. All right, let's weigh that one. There you are. There it goes. All right, let's weigh it. That was pretty good, though. All right, let's weigh it. You guys did great. Look at this, guys. The paper cut before the composite gave away. So the string on there actually cut into the paper before it had a chance for that composite to give away. That's awesome. Your composite held up great. How much?
106.55.
106. That's amazing. Good job, guys. And this was the one you built?
Okay, so it looked like they were very successful with their composites.
The kids did a great job building the composites. Actually, we've got one of them that's going to share their results. So,
Okay.
Leah, you want to share your results with us
Terrific.
on your experiment?
Our composite increased the amount of water, of how much water it was held into the jug.
So there was more, it held more weight. Which one worked the best?
The two composite with the fabric between them.
Okay, so the big composite
Yep.
worked
Yeah,
work
the
the best?
composites really increased the amount of strength that they were able to hold.
Okay, and do you want to start us off with a question?
Yes. Since I'm in 8th grade, how can composite help me in my everyday life?
So how can composites help somebody that's in 8th grade?
Oh, well, sporting goods in general, there's a lot of stuff that's coming out. It's not just what we showed here. It's tennis rackets, golf clubs, hockey sticks, all sorts of things, bikes now that are all lighter. You'll find that they actually might be in some of the electronics that you have, for instance. And if you've got somebody that's driving you to and from, hopefully, as we get more composites in the cars, it's helping to reduce the gas bill, the fuel bill.
And now we have an online question. Why are composites an improvement over metal for building airplanes?
Well, what we saw earlier today was a demonstration of really how durable they are, because you have hail balls and things like that, but you especially have people that drop tools and stuff like that sometimes. So that's just one thing. They also, they don't corrode. They're more fatigue resistant, which has to do with when the pressure goes out and in, for instance, on the airplane. And there's lower maintenance costs. This is like for the Dreamliner, we're talking 30% lower maintenance costs because all of these different things that add up. And the other thing is part count. We have almost 2/3 the part count because we've got these huge integrated structure barrels instead of, one barrel might be replacing over, 1,500 pieces of aluminum that would go in a normal fuselage.
How many parts are in a Dreamliner?
Around 2.3 million. And that's low compared to other airplanes.
And
they start at 3 million up.
And we have another online question. Why are
It's the same question.
we have
There we go.
Where have composites made the most difference on an airplane?
That's a tough one. So I'm going to go with the combination of the exterior. We've had composites on the interiors for a very long time. And so with the Dreamliner, we went on the outside. And it wasn't just that it was lighter, it was because you can shape it from an aerodynamic point of view as well, and you can put some sections thin and some sections thick instead of having to use the same thickness everywhere, because you have different requirements and different needs in different places.
Okay, so the composites are great for the outside, but our friend Dan out at Seattle is going to tell us how it's making a difference for the passengers on the inside of the Dreamliner.
Welcome aboard Boeing 787 Dreamliner ZA003 here at the Museum of Flight at historic Boeing Field in Seattle, Washington. Now we're going to be taking a look around the interior of the aircraft to show you some of the passenger accommodations that have been made possible by the composite structure of this aircraft. As you make your way to your seat on the Dreamliner, there's several things that will become apparent to you very quickly. The first thing you're going to notice is how quiet it is aboard this aircraft, both on the ground while you're waiting to take off, as well as in flight. The second thing you're going to notice is the incredible feeling of spaciousness that the aircraft provides to you as you make your way through your flight. This is facilitated by the fact of the overhead lighting. Here you see, and behind me, the blue lighting effect that is prevalent on the aircraft as we have her sitting here, but there's also a wonderful rainbow effect that has a very calming influence. Something that's far more subtle, however, that you're not going to notice right away is the incredible degree of atmospheric control that the aircraft has as a direct result of the composite structure of the aircraft. You're going to feel as though you're flying at a lower level, and the humidity controls aboard the aircraft are directly controlled by the crew itself. It's going to feel much more comfortable. But last but not least is the overhead bins, something that we're all familiar with. They deploy very, very nicely aboard this aircraft, and more importantly, they're quite large. These are all a direct result of the composite structure of this aircraft. One of the wonderful passenger amenities provided by the composite structure of the Dreamliner is not only the relative location, but the size of the passenger windows that you'll find at every one of the passenger seats. To my left here, and I'm sitting on a seat at the relative elevation of most of the standard coach seats and first and business class seats on the Dreamliner, you'll notice that I don't have to do this or this, or this, in order to look out the window and have a panoramic view. Remember those pesky pull-up, pull-down shades that you found on conventional airliners? Not going to find those on the 787 Dreamliner. Instead, every single passenger aboard the aircraft, using this very simple control right below the portal right here, controls the relative clarity or opaqueness of their individual window. You can darken it, you can lighten it, and the relative degree of darkening is completely at the control of the individual passenger. They can also be controlled from a central location by the flight attendants and the crew if necessary. But in the final analysis, every passenger has complete control over the relative clarity of the portal that they're sitting next to.
So Arlene, one of the things that really intrigued me when we saw the inside is the larger windows, because you know we're used to the small ones. How come we can make the larger windows on the composite airplane?
That really goes back to that whole video. We've got this huge composite barrel. It's all one material, but we're able to lay in extra material around the window frames.
Oh, okay.
So we don't have to penalize the whole thing for just those holes.
Okay, that's interesting. And we have some audience questions, so let's start with our audience.
How long does it take to bake a composite?
How long does it take to make a composite?
Well, a lot depends on what the size is, and so there are some parts you could make in a half an hour and then you bake it for a few hours, and some could take days. Depends on what your size is and how complex it is.
And we have an online question. What type of composite products can we expect in the future? Has the space agency helped in the development of composite materials?
So I'm going to take the second one first, because the space age really was instrumental. It was super important, especially early on, for developing the materials. And you'd be surprised at the number of things that you're working on in the space arena that ultimately end up in the everyday world.
Okay.
So very important. And we do make things that were metal rockets now. We'll have, for instance, composite parts too. So we're making those lighter and easier to lift.
Okay, so we have one quick question.
Can anything damage a composite?
Can anything damage a composite?
Yes. So although we hammered it, we were designing for people to drop tools and that sort of thing, right? But if you had something like a forklift and you run it in, it will still go through the side.
So they're not indestructible.
They're not indestructible. And that reminds me, there are a lot of different types of composites and plastics, and I want to warn you, we custom designed the material that you saw us hammering on. It doesn't mean necessarily that every composite you see you can treat that way.
Okay, well, thank you so much, Arlene. This has been really very educational, and that is all the time we have for this STEM in 30. I'd like to thank our friends at the Museum of Flight in Seattle for the wonderful tour of their Dreamliner, and my new co-host Marty. And I'd also like to thank the Boeing Company, and I hope to see you all again back here next month for STEM in 30.